Welcome back, my math enthusiasts. So here we are looking at the matrix of a linear transformation. And now, when a linear transformation arises, either geometrically or verbally, we're oftentimes concerned with finding a formula for the image of vector x under the action of our transformation. Now, to find such a general formula, we need to observe that our transformation is completely determined by how it affects the columns of the identity matrix. And now we've begun to look at this in the previous section when we were introduced to linear transformations, when we looked at the definition and the properties that arise from this definition. So here we're going to start to look at this idea in more detail to help us establish this general formula and the standard matrix of a transformation. So to get us started, before we jump into our arbitrary case, I want to warm us up by looking at the general formula for a transformation in R2. So we are looking at finding a general formula for the image of vector x under the action of t, such that t is a linear transformation from R2 to R2. So again, we are supposing that t from R2 to R2 is a linear transformation. So noting that this is a linear transformation, we'll keep in mind our definition and the general properties that arise. We also want to go ahead and let vector x be some arbitrary vector in R2. So the first thing that we want to do is take this arbitrary vector x in R2 and decompose it into a linear combination of the elementary vectors. Remember, those elementary vectors are the columns of our identity matrix. So here we go. We know that vector x is in R2. So this vector has two entries, x sub 1, x sub 2. And we know now that an equivalent way to write this is as a linear combination of the elementary vectors. So we have that weight, x sub 1, multiplied by the elementary vector e sub 1, plus our weight, x sub 2, multiplied by the elementary vector e sub 2. Now, we, again, are trying to find a general formula for the image of vector x under the action of t. So, using this new decomposition and keeping in mind that our transformation is linear, we can do the following. So we have the image of vector x under the action of t. We now know, of course, that vector x is equivalent to this linear combination, x sub 1 times the elementary vector e sub 1 plus x sub 2 times the elementary vector e sub 2. And now again, since this transformation is linear, we can decompose this image. We can rewrite this as the sum of the scalar multiples of the images of each elementary vector. Again, that's by definition of a linear transformation. Now, also keep in mind that what we have here is a vector equation. And we know from our equivalence theory that we can rewrite a vector equation in the equivalent matrix equation by taking the vectors and putting them into a matrix. So we can rewrite this as the matrix with the column vectors defined as these images. So we have the image of the elementary vector e sub 1 under the action of t, and then our second column is the image of the elementary vector e sub 2 under the action of t, multiplied by vector x. We have x sub 1, x sub 2 as the entries of this vector. And so this is our standard formula. This is going to be defined as matrix A multiplied by vector x. And we'll make a little love note here to ourselves that this is where this matrix A, whose column vectors are the images of the elementary vectors under the action of TR transformation, this matrix is called the standard matrix of T. So this is the general formula for the image of vector x under the action of t. And now that we have seen this, in the cute case where t is a linear transformation to R2 to R2, we need to go ahead now and extend this to higher dimensions. So let's go ahead now and take a look at the formal proof for the general formula for our image of vector x under the action of t.